We're ready. Good afternoon. Hi, welcome. I'm Ron Bernstein. I am chairing this session on the built environment, interoperability, integration, and grid services. So this is a kind of maybe a little different for an HR Expo meeting, but let me give you a little background. The session today is sponsored by the Gridwise Architecture Council. Anybody ever hear of the Gridwise Architecture Council before? One person, and you guys should raise your hands. We don't care. So the Gridwise Architecture Council is a think tank that's sponsored by the U.S. Department of Energy, looking at the North American power grid and the future state, the grid architecture, and the status of how we're going to maintain a stable power supply in North America for the next 50 years. So we are a elected body of industry experts. Most of us, some of us are, some aren't in the grid world. But we have a collection of 13 different members from all walks of our expertise in the industry that look at policies, regulatory, technology, and all the aspects that go into driving grid changes. And there's a lot of them happening. So we're trying to help influence that, and I'll talk a little bit more about through that. But we have a partnership with HR Expo and now with ASHRAE that GWAC, we call it GWAC, and these three organizations are working together to bring more educational programs to the conferences here, maybe a little bit outside of the normal HVAC and ASHRAE world. So with me today, so my background, I'm a consulting engineer. I do very specialized consulting with large organizations building enterprise systems that converge IT, OT, system integration, interoperability, and grid services. So that's the world I live in. Let's get the slides to advance. There we go. So our panel today, that's me. I'll moderate and bring our guests up. We have two guest speakers today. We have Sean Chandler, who's the executive director of CAPCO. He is also our incoming vice chair. I've already elevated you, even though so the vice chair of the council, of the Gridwise Architecture Council. And then we have Matt McDonald from managing partner at GWC. Oh, no. What happened here? Oh, there's a spelling mistake there. At Current Energy. And both Matt and Sean are council members that work in the regulatory policy, transportation, and you're going to hear about those different areas. So a little bit beyond the normal world of ASHRAE, but I think you're going to find it very interesting what's happening in the grid and what's changing with things like distributed energy resources, solar, PV, wind, and EVs are changing the way the power grid is working or not working. So that's what we're going to talk about. So that's my little background on GWAC. I'm going to give you a 2-minute video. Watch this. There we go. Because we spent some time and money to create this.
Who is building the grid of the future? Well, there's no single organization. The task is just too big. But the Gridwise Architecture Council is shaping the guiding principles or architecture of a highly intelligent and interactive electric system. The council offers concepts and guidance to stakeholders who are part of the evolution of the power grid. Convened in 2004 by the Department of Energy, the GWAC has already had a big impact on interoperability standards and transactive energy concepts. The Council envisions the societal benefits of a decarbonized, decentralized, and democratized electricity system that will supply the energy needs of today and for future generations. The power grid is evolving. New technologies generate, control, and use electricity. And coordinating these distributed, sometimes customer-owned, assets is complex. The 13 rotating council members have a variety of backgrounds within the electrical system. They are thought leaders in utilities, buildings, policy, engineering, software, consumer advocacy, and more. The council bridges these communities with their individual perspectives to create an inclusive vision for the future grid. To prepare for the grid of the future, the Grid-Wise Architecture Council defines, clarifies, and recommends architectural principles and concepts, and provides guidelines, position statements, and checklists for decision makers. Workshops and meetings identify challenges and solutions and provide feedback to the Council. The Council seeks input from various sectors and stakeholders to create a consensus vision for the future grid. If you're interested in helping shape the vision for a decarbonized, decentralized, and democratized electricity system, we'd like to connect with you. Get started by joining us for GWAC monthly meetings, which are listed on our website.
We kind of thought that was a fun little video. That's not something we would normally do, but the marketing department at P&L said, "Hey, try this, see what you think." So that's a little bit about who we are and why we're doing this. We've done, since I've been involved, we've done lots of white papers, lots of postings. We've done videos, we've done trainings. We participate in RE+, which is the Renewable Energy Conference. We've held symposiums over the years. We've developed quite a few work products that have helped shape regulatory and policy across the industry. And we're doing more. And we're going to talk about 3 of those today, which is the highlight of this session, of the new work products that the Council is involved in. So the first one, I'm going to summarize them very briefly, 1 slide each, and then I'm going to have the 2 leaders of 2 of those 3 work products actually come up and speak to us today about the details of those. So the first one is systems thinking for regulators. So one of the challenges in the grid is that it's in many cases, a very regulated environment. The grid is all interconnected for the most part, except for maybe Texas, all the way through up into Canada. And so that interconnection has some roles and responsibilities that if you are a producer of power, a generator of power, or if you're managing the distribution of power, or if you are a consumer of power, that there are some basically rules of the road that you have to adhere to in order to maintain a stability of the grid. And the stability of the grid is measured in microseconds, literally microsecond adjustments of how you bring on power, how you do phase loading, power factor. All of that is done at that microsecond level. But the rules that we have to apply have to filter down from the days, weeks, months, hours, down into the minutes and microseconds. So part of this work product is looking to underscore the complexities of facing the electrical system, especially as we're bringing on new generation sources. So if you remember, the power grid, when it was originally designed, was a one-way flow of electricity, one-way flow of electrons from generation to load. That's not true anymore. Any folks have solar around their house? How about an EV? Anybody run an EV car? All right, so you can produce power back into the grid when you plug in your battery into a charging station that takes battery out. I have solar on my house. I feed into the grid. My solar doesn't feed my house. My solar feeds the grid. And then I consume that through a financial or transactive process on the energy. I get a benefit from that. But I can't just flip the switch and turn my power off from the grid and just go on solar. That's not how it works. That's part of the regulatory policy. And many of these new cogeneration plants and microgrids are affecting the way the grid is structured. We'll talk quite a bit about the grid architecture and those structures. So that's one project that Matt is managing. A second one, which unfortunately we weren't able to get one of the speakers here, is on applying the concept of bridging back from the future. So I'm going to talk about this one a little bit more. It's basically what's the grid going to look like in 25 to 50 years, based upon the best guess of what we know now, and where are we today, and how do we get from here to there? I'll talk about that. And then the last one is one that Sean's working on, which is the grid architecture concept model for transportation electrification. So, in ASHRAE, there's a big push on decarbonization and electrification of buildings. Well, the same concept is happening in the transportation marketplace. So as we bring on more loads, more residual storage capacity, how can we use that, and how is that going to affect the grid? And Sean's going to talk more about that. So how has the electrical system changed over time? Well, there are a lot of pressures. So there's environmental pressures as well as consumer expectation and sentiments. Very often the way policy gets orchestrated is on the current cultural philosophy. What is our current philosophy? Well, our actually philosophy may have changed over the last couple of years as to whether we're looking at decarbonization and reduction in greenhouse gases versus something other than that. Should I say that? I would say that. Let's stop there. So the cost of distributed energy resources is going down. The cost of conventional sources of power is going up. And at the same time, there's an exponential growth in technology. So these are all the things that factor into the changes that we're starting to see. More and more distributed resources, more and more opportunities for community generation, for individual generation, even for buildings to have generation or cogeneration as part of the integrated environment. It's blurring the lines of that traditional grid boundaries and increasing what we call edge devices, edge power, edge demand. We also have more batteries for storage, so we can change how the structure of when and how power is provided. And it's all done through this sort of looking through the lens today of building electrification and the impacts of that on the grid. So one of the things, and I should also mention transportation fits in there too. One of the things we looked at in the council is we said, we've got to take some sort of vision setting. We can't sort of predict the future unless we kind of put a stake in the ground. So we started looking at a 25-year event horizon. So what is the grid going to look like for the North American power grid in 25 years? What step changes are needed in order to get us there? And is our vision achievable, believable, and acceptable? If you've ever done mission statements and vision setting statements, one of the key foundations of that is it must be at least 50% believable. Doesn't have to be 100%, but at least 50%. Don't go doing a vision that, we're going to be on cold fusion in 10 years. No other source. I mean, that's not believable. So we have to get to something that's believable, acceptable, and achievable, at least with what we know now. And we can change that over time through those step changes. And then we have to look at the market conditions that are going to get us there. Where are we? What's the cost of energy? What's the cost of energy in California versus Nevada versus like New York or Hawaii? Those things vary around the country substantially. So what do those market conditions look like? Who are the stakeholders? So we'll talk a lot about stakeholders. I'll leave that for later, but who are those targeted stakeholders that are going to help make those decisions? The policymakers, the program entities, the utilities. And then what's going on beyond that 25 years? If we get to 25 years, what is it going to look like for the next 50 or 100 years? Are we moving in the right direction to be sustainable in 100 years from now? Well, that's a heavy lift. That's where we start looking at 50 years. So this is the focus of the council. We evaluate, we advise, we educate, and I put up some benchmarks. So this may be some interesting to you. These are some of the benchmarks that I did this presentation with this slide a couple of years ago. And this is the 2020 primary energy source consumption by energy source. I have the 2024 number that I'm going to overlay on top of this. Look at the difference. Specifically, look at renewable versus petroleum and natural gas. So this was the consumption, maybe roughly 12% back in 2020. And here's the one in 2023 that we went down to 9%. That might not seem like much, but in my mind, we're headed in the wrong direction. And this is just from 23. Where are we in 26 now? I don't know the numbers. We don't have any place to get the numbers anymore. But stop there. U.S. production. So this is the production, a little hard to see there, but if you look at it all the way from hydro, renewables, other renewables, nuclear, wind, God, I can't see it. Solar, coal, fossil fuel, and petroleum. These were some original numbers, and then I found another chart, which is even more recent, on where that shift is happening. So there's definitely a shift happening over as philosophy and social structures are changing. And the last one here is looking at, sorry, too farther. Looking at the generation capacity additions to the grid. Where are new projects coming in? Where are new utilities or new generation being applied for? You have to apply for that. Where's it happening? And if you look again at the difference between solar and wind from 2021, and then you look at it from 2024, significant difference. Significant difference. Much more on the battery storage and solar versus here wind and solar. And some natural gas. We come back to the natural gas, significantly less on the natural gas. So what all of this is saying that our makeup of the generation fuel sources are changing as we're changing technology, as we're changing philosophy, as we're changing the direction of the market, which is affecting how we have to think about this 25 years from now. We can't predict what's going to happen in 2 years from now, even just looking at these slides. How are we going to predict from 25 years? Well, we have to do something. So I put a stake in the ground. This is sort of my opinion that we've kind of started bouncing around. A 90% reduction in fossil fuels in 25 years from now. Grid architecture shifts primarily to distributed systems versus central systems. Centralized system means that big generation, you as consumer, one-way flow of energy. Now, we're moving to a much more distributed, lots of community solar, lots of community battery storage. Over 25 years, we're going to see a lot more of that. We're going to see upgrades to distributed energy resources. Anybody have solar on the house besides me in the room? Just me? One? Two of us have 3 times solar in the house. I predict that we're going to have a whole lot more solar. We're going to have a whole lot more batteries. The costs are coming down dramatically. It's going to make more sense over time. And that's going to also affect grid reliability, resiliency, and sentiment and cost as the structure of the grid changes. Transactive energy. This is a concept, I won't spend much time on it here, but it's a concept that GWAC promoted for many years that says energy is going to be transacted based upon a source and a destination, and maybe another source and another destination, and maybe a whole bunch of destinations and a whole bunch of sources. And that the transactive ability to use something like blockchain, anybody familiar with blockchain, to transact the flow of energy in real time and manage the cost of that can be done in a transactive model where it's not just, I'm going to send you a bill based upon your meter reading at the end of the month. So that's the concept. So we're going to see more of that. It's already happening. We put a stake in the ground to see what we might see some solar-based energy or some safe fusion-based energy sources demonstrated. We're already starting to see a few, but we said that might be a game changer. No coal-based energy sources on the U.S. grid. That's know what a BHAG is? A big, hairy, audacious goal. That's a BHAG. But put a stake in the ground 25 years from now, at least when we did this 5 years ago, that was an intention. Start removing the coal. Huge greenhouse gas producer. Natural gas sources reduced by 50%. From 2020, grid load increase. This is the big one. We're shifting, if you look at the load profiles of where we've been over the last maybe 50 years to the last 5 years, we were flattening out on our actual demand for energy until about 5 years ago. What happened? Data centers. Rocket ship. Data centers have increased that load growth, and electrification of transportation and now electrification of buildings is going to increase the generation need capacity by 20 to 40%, if not more. And continued electrification of buildings, cities, transportation, all of that is part of our stake in the ground. Well, you heard in the video the 3 Ds. I'm actually going to give you the 5 Ds. These are the guiding principles to what we have to think about when we say we're looking at a future grid state. 5 Ds include deregulation. So less regulation on source of energy on the generation side, the digitization, we're going to have more digital data available. We'll be able to transact energy in a digital capacity more. Decarbonization, talked a lot about that already. Decentralization, no longer the central utility and you as a consumer. No, you might be able to pick from 5 different utility sources, or you might have your own solar or a community solar battery program. Democratization, that's a big one. Democratization basically means fair access to everybody, not just the rich, not just the urban, but everybody going all the way out to rural, that there's a democratized, a democratic process for access to energy. That's a disrupting, that's happening now with data centers, which we have a little time, we'll talk about that. That data centers are going behind the grid and attaching directly to the generation side of a generator and bypassing all the regulators and just taking energy right out of the utility and putting a data center right next door so that they don't have to deal with all the regulation. But that then says, hey, there's 20% less energy from that power source for you and me for our homes. Our prices just went up. So that's a democratization issue. So that's the future grid state. We are looking at this model. We use this model of bridging back from the future. We think we know what it's going to look like. We're here today. How do we get there? And how do we make sure we don't miss the bridge by building from both sides of the harbor, like the Sydney Bridge, like this example? How do we get there? That means we have to take incremental steps backwards to say we're not there yet, but we should be here in 20 years. We should be here in 15 years. We should be here in 5 years. And here's where we are today. So we're looking at that as part of this bridging back from the future. And as part of that, we cause looking at the chasm, the needs for how to operate the grid safely, reliably, and with resilience, with more weather changes. Every time we get a major storm and the power gets knocked out, how quickly can we respond to that? If you have more and more generation sources, that causes more and more challenges for the linemen working on the system. Do we need to rethink how demand side interacts with supply side? Well, this is part of another session we're talking about tomorrow on how does the building interact with the grid from a grid demand side management or an open automated demand response side. Talk more about that in a minute. And then do we need smarter, interoperable, more integrated buildings? This is a big piece of it. Buildings still are the largest sector of power consumption in the market today, and it's growing rapidly as data centers are coming online. Last numbers I saw, it was 73% of the power grid fed something related to a building. 73%. That also includes all those EV chargers that the bill for the EV charger goes through the building's power source, the power meter. You don't see a power meter on an EV charger. You see a power meter, something connected to a bid that has a computer that's talking out there. It sort of goes through a building related system. So we have a bunch of players. We have regulators. We have utilities. We have service providers. We have consumers and prosumers. And they all have different interests. They all have kind of their modus operandi. And somehow we've got to bring all these players together to have some meaningful conversation about how a change here is going to make a change over here. So I won't go into details. That takes a lot to go through that, but there's a lot of pieces there. And then when we talk about building to grid, so how do we get the building to grid to respond better to grid signals? How do we make the buildings more grid interactive? We've got to look at what load shedding and demand response. It's a spicy topic. Price, that was reading the two together. How all of that influences the operation of a building, the sequence of operations. What mode do we put the building in? Can we do load shedding when the price is a factor? Can we do that in real time as part of our normal building designs? And equipment reporting on demand, can we feed back to the grid that yes, we can shed load. We can shed so much load and we can do it in 15 minutes, but we can't do it in 2 hours. So the grid is going to want to know more granular information as a source of grid control and management. And building integration can help with that dramatically. So we've got other factors in there. We'll go through them all. How the grid interfaces with building management systems for capturing metering data, sub-metering data, analytic data, and then on-site distributed energy resources as it relates to the grid, and then the impact of the design of central plants and power equipment and schedules as related to pricing signals coming from the suppliers. Predictive applications for energy demand and balancing, like price, weather, and scheduled events. And then we start seeing connected buildings with more and more electrified equipment. So electric heat pumps are a big one. Solar and batteries on the sides of buildings, backup batteries as part of a manufacturing or process. EV charging systems, electric hot water heaters, all of that is bringing on new loads that we have to balance as part of our building management system. So there's this concept that the relationship between the equipment that's in a building and the grid is this big spaghetti nest of interactions. And this is what we refer to in GWAC, we coin the term grid architecture or grid interactions that is very complex, and we have to find a way to simplify it. So we're working on things, PNNL does some work with energy services or this energy services interface to try and reduce that complexity that gives you only the information you need to know. And a lot of that is about interoperable communication, taking a BACnet IP network and taking the data points that are relevant for the grid and bringing those in through an energy services interface, standardizing them across multiple buildings and multiple domains, subsystems, and then presenting them in a way that I can do something with intelligently, rather than having everybody to figure out the spaghetti nest over here. There's a term we use, it's called, get this, delaminar composition. So we're going to take the many layers, the 7, 8 layers there, we're going to segment those, we're going to delaminate them, and we're going to deal with each layer independently with still keeping the whole thing in mind. That's a whole course we took in grid architecture. I took it, I'm now certified. I'm not sure I understood half of it, but this is, you know, the world of modeling of grid systems is very complex. So, in summary, for my part, will buildings become part of the grid problem or the solution? I hope we're being part of the solution. We're already doing some work. I'll put a plug in for ASHRAE 1.4 and ASHRAE 7.5. Both groups have work going on in building to grid integration, specifying building to grid integration and interoperability within building projects. And having something in there about load shed, demand response, and grid signals is a good part of a good Div 25 spec. We want to manage the automation system loads responsibly based upon the particular environment's load shape and where you want to offset your loads based upon what's happening on the grid in your area. I live in California. We have something called the California duck curve. Anybody ever hear of the California duck curve? It basically says in the morning, you're going to have a low demand for power. As you go through the day, the power demand increases, so the price goes up. And then at the end of the day, it kind of ramps down. And then now you have this block in the middle where the sun's out, and we have all this solar, and the available power demand drips because everybody's got their solar on, and then it ramps up again as soon as the solar comes down, and that thing is dipping down more and more, and we've got to start leveling that out because the grid can't handle the duck curve. It looks like a duck. I think one of you has a slide on you to talk about it. Okay. So grid operators, regulators, and policymakers are looking for a collaborative impact on the design of buildings and how they're going to be able to help manage that. GWAC is developing thought leadership. Please join us at gridwiseac.org. Lots of videos, lots of discussion there. We welcome you to that. And that's the end of my piece. Any questions, real quick? We have time for questions. Good. All right, let's move on. All right, next up, Sean Chandler is going to come up and talk about smart buildings and the future grid perspectives. All yours.
I'm sorry. Hey, everybody, good to be here. If you feel the need to raise your hand at any time, I also teach electrical engineering, and if you just want to ask a question, it's burning in your pocket, just raise your hand and we'll pause and we'll talk.
How does electricity move?
How does it's a wave. It's a wave. There's no electrons actually moving. All right, let's just jump right in. So first, I want to make sure that I'm pulling this all back to buildings. Everybody here is really thinking about buildings and the equipment. I was the chair of the IEEE Smart Buildings Loads and Customer Systems Technical Committee. I was the founder of that committee. That's the largest standards organization in the world, and we make standards. It's electrical engineers and electronic engineers make a lot of standards for the grid. We also make a lot of standards for the devices in everybody's pocket. Those devices wouldn't work if it weren't for IEEE standards about how wireless connections function. So this idea about smart buildings, that's really important to my presentation today. So there are a lot of key trends that are shaping what's going on in smart buildings today worldwide. So we're going to talk very briefly about that. We're going to talk about energy and smart buildings and why you should be very interested in this. We're going to talk about smart building coordination with the grid and why that's important. Building really on Ron's presentation. We're definitely going to talk about the smart building as a microgrid. And a microgrid just means that it can form a whole grid of its own. And then we're going to talk about how grids and buildings and the systems in those entities, those structures, how they integrate. And that's very important today. It's important to all of the 25 or so controls manufacturers and all the device manufacturers that I just spoke to over the last 3 hours. Just a little bit about that. I talked to so many folks, I almost lost my voice, but I don't recall speaking with any of you, but I'm sure I've talked to someone else that you've talked to today. And what I found out is that this is a real thing, but nobody knew what a virtual power plant was. There was no one among all of the smart building folks that I talked to, all the different controls manufacturers that are running building management systems, and all the equipment that runs on different types of sensors that integrate your chillers and your pumps and your rooftop units, all your commercial water heating. Nobody knew what a virtual power plant was. So we're going to definitely talk about that. And then we're going to talk about grid optimization. All right. So first, the big thing here is that the grid is changing because of the location of the generation. The grid has been around since the 1870s. And the very first transmission of electric power was up in Portland, Oregon. And they were just running a series of DC arc lamps for the city of Portland, and based on basically it was a water hydro system. And since then, what's happening is that those centralized plants, and if you think of a power plant in your city or near a town, if you can't think of one, that's normal, and that's because it's really far away from you. They were built far away from the population centers for a reason, and it's because they were smelly. Number one, they put a lot of things into the area that people didn't like, and they were loud, real old equipment. It was super loud, and so nobody wanted a power plant in their backyard. And in the energy industry, we have a name for that. It's called NIMBY, not in my backyard. And so you'll find that a lot of these power plants that you see, they're just not around. So why does that matter for smart buildings? And it's because up to 50% of the energy generation is now moving into the building. It's moving away from the power plant and into your backyard because it's quiet and it's sustainable. And probably the most important thing is that it helps you. You actually pay less money if it's distributed for a lot of reasons. Most importantly, because of the losses. If you have a power plant way out there, it loses up to 10% of the power just transmitting it from that power plant into the city. And so this idea that a distributed system is more effective is definitely true. Buildings are microgrids with natural characteristics. Here you can see that solar panels, vehicles, wind turbines, ice generation, like emergency backup generators that are in almost all critical building function systems, they're all in there. And then batteries, of course, those are all inside the building. And then the building is getting most of its power from the grid. But that doesn't mean that it needs to in the future. That's important. And second, that these new operational paradigms, this idea that there's energy service providers who can aggregate them together and make a virtual power plant So if I take a system from your building and your building and your building and your building, and I bulk them together into one system, that's a virtual power plant. And if your generation goes up, you can serve load anywhere in the whole grid because the whole grid has to turn together. All of the generators in the whole United States are turning exactly together. Exactly. All of the waves have to move together. If they don't, the generators explode in this brilliant display of sparks and gas. It would be really something to see. That used to happen in the old days, but it doesn't anymore. And so here, this idea that we have to get energy markets involved, because what happens if you don't have enough generation for your utility? What do? They go out and they buy it on a market. And some other person far, far away from your load center is making that generation. And so these are very important concepts for us in the smart building, in the building arena. And all the equipment that you install today, it's important because it can act on the grid. And here's how much of it. 1 billion megawatt hours of controllable load annually in your commercial buildings alone. 1 billion megawatt hours. Now, a megawatt hour will run basically 1,000 homes for an hour. And this is 1 billion megawatt hours of controllable load. In the United States, $241 billion were spent just in the commercial energy sector in 2024 to pay for that energy. And it's going to increase by 40% over the next 25 years. That is a massive increase in load. Most of that is because of electrification. Electric water heaters, electric heat pumps, electric. So you're seeing just a lot more load, and data centers, of course. With the controllable loads, out of the 7.5 quads, and a quad is a quadrillion BTUs of gas, basically, all of those different commercial types of buildings, half of it is controllable. And here's why. Because ventilation, space heating, and cooling is about 33% of it. Every building out there uses about 33% of its load on those three, on ventilation, space heating, and cooling. Computing and lighting is 13%. Water heating is just 3%. But if you add all that up, it's almost 50%. And so that means if you can control ventilation, space heating, and cooling, which you can, most of the control manufacturers out there have systems that can be controlled. Computing and lighting can definitely be controlled. You can adjust it down just a little bit. Like even in this room right here, if we could adjust these lights down just a little bit, it wouldn't impact anybody. We could do that. And then finally, water heating. You can heat it up when you know you're going to need it, and then a little bit over temperature, and then let it ride through an event. All those savings can amount. That's shifting, shimmying, shaping, and shedding the load. Those are all industry terms, but I'm going to move on. If we coordinate across the grid, then we can create a platform that can control all the buildings together and make virtual power plants out of them. And here's what I really want you to see is that if you turn off your loads just a little, and I do that in a million other places, that is power plants and power plants worth of generation. Why? Because when the load is going up, if other people turn off, then you can stay at the same amount of generation that is coming from the power plants themselves. So demand response to shut off your demand as load is going up means you can keep the same number of power plants. That's why it's called a virtual power plant. You're not really generating electricity everywhere. Now, storage can generate. And internal combustion engines, they can generate. Solar, it can generate. Wind, it can generate. There's a lot fuel cells, they can generate. So all these distributed systems, they can generate too. But you can get the same effect just by turning things off. And if you bulk all that control together, a market operator and a grid coordinator and a customer all connected through the smart building or a big real estate portfolio can really help the utility, and it will lower your rates because they do not need to spend a bunch of money for a new power plant. Let's keep moving. All right, so virtual power plants, collections of resources across the grid in many different buildings. Your buildings, the buildings that you put equipment in every day, The buildings that you're selling equipment to every single day, those are the buildings we're talking about. It's all of them. The residential, the commercial, and the industrial. We're just talking about commercial today. But generally, most of the equipment that you're putting in now has variable frequency drives, VFDs. Raise your hand if you know what a VFD is. Most of you do, because VFDs have been around for a while. And it really helps your customer. They're buying VFDs because it saves them money. But if they do it at the right time together, that's where we really save money. Because right now we have all this jumbled chaos in the grid, and the utility has to pay for all of that and ride through all the different kinds of events. If you get all the buildings to work together and get everybody to coordinate, that can make a huge difference for civilization. And so that's why these virtual power plants are important. Your EV charging, your HVAC, your lighting controls, your energy storage, all your generators, and especially your VFDs, fans, pumps, chillers, heat pumps, all of it. You connect it all together, and all of a sudden you have all these buildings that are connected together talking to the utility, or maybe a service provider, maybe an aggregator. And then an aggregator can talk to the utility. There's a huge new market out there for doing this work. All right, so because the smart building is a microgrid, let's talk about what that might look like for each of you. First off, let's look at the microgrid inputs. What's in a building that we care about here at this conference? Ventilation, HVAC, lighting, water. The big one in the room, it's the big gorilla, electric vehicle service equipment, fleet charging. I know that Ron asked, but I didn't turn around in time. How many people have an electric car? Anybody? A few of you? About a third of you have an electric vehicle. Your electric vehicle has a 75 kilowatt hour battery in it. 75 kilowatt hours. Your house uses about 1, maybe 1.5 kilowatts per hour. You can run your house for 3 days off your car. 3 whole days. If you run it down to zero. Where's all that juice coming from? Most people want to charge at work. Why is that? Because the electricity looks free. It's because the building is paying for it. It doesn't look like much when there was only 1% of people owned an electric vehicle. Right now, we're between 5 and 10% of the population is looking at buying an electric vehicle because of how much less it actually costs to drive that car. You drive, we're talking like 10 cents a mile. 10 cents a mile instead of $1 or maybe 50 cents a mile. There's huge savings because of the difference between gas and electricity. So that transportation is a big deal as it starts to shift to the building. And right now there might only be 1 or 2 chargers at those buildings where you're parking that car right now. Maybe 1 or 2, maybe 4, maybe 5. Even my airport that I fly out of most of the time, it's got 6 chargers. They're always full. In the future, there'll be hundreds of them. And that's a lot of load. It's as much as the whole building load. So you got to be preparing for that. The environment, the occupancy, you care about occupancy in this building. That's why we've got all these fancy sensors everywhere. Temperature, you care about the temperature in the building. You care about ducting and zoning in the building for a reason. Because it costs a lot to heat every single space in the building. It costs a lot to ventilate every single space in the building. If you can manage that, it saves money. That's why we're selling equipment at this conference regarding those tools. If you join them all together to work together and make sure that they're matched up with the building occupant needs, then you can really change the way that the grid works. Finally, the humidity, the time of day, traffic around the building. Imagine the building knowing how many cars were supposed to arrive and having the batteries ready for the EVSE that needed to charge. Finally, smart city IoT. Not a lot of buildings are talking smart IoT yet, but it's definitely on the way. And then the grid. Right now, the building has a meter, sometimes more than one. Regional grid performance indicators matter to the building because if the building drops its loads as the price goes up, it saves everybody money in the long run. And that's because of how much it costs to pay for the power during what's called the peak load the highest use of energy in the day, which is between about 8 p.m. and 10 p.m. at night. It's not even in the middle of the day. There is like a little mini peak that happens in the morning when everybody gets to the building. And then there's a peak right before everybody goes home because they're trying to get as much work as they can right around 3 o'clock in the afternoon before they turn everything off. But all of that data, if it goes to building operations, your building management system could have all those controllable resources. It could couple it to the grid, coordinate with the utility through what are called distributed energy resource management systems. And then finally, the virtual power plants can feed their sensing into the utility and everything works together. And all of a sudden we have one big system that is in harmony. It's the largest machine in the world, the electric grid. So you're just making that machine a little bit bigger by extending it past the meter into the building space. All right, I'm going to talk just very briefly about the architecture here. I'm doing good on time, and I want to leave time for questions. First off, we have all these different layers that architects, grid architects, think about when we design the grid. And it's really about, and notice at the very top, there is no such thing as a grid without policy and regulatory. It's one of the most fundamental things in the grid is dealing with regulators because it's a public good. Everybody needs it, more now than ever before. They thought it was important in the 50s, the 1950s. Nobody can live without that brick in your pocket. You just need your electricity now. No one lives without their computers. So this idea that a VPP, this virtual power plant platform, it has to deliver flexibility to the grid and participate in the market, and it needs to satisfy the regulators, and way down at the component layer, it needs to satisfy you. What were to happen if this room right here were to shut off the ventilation, turn off the lights, and the temperature goes up by 50 degrees? How many people would stay even 1 second? None of us. You'd be out that door quicker than you could move your feet. That's the point, that it's the occupant in the building that matters. We have buildings because it's places to collaborate and work together. But the building, if that isn't working for people, they're not going to want to be there. So you got to make it work for people. So that joining from the policy layer to the business layer of the building, to the functional layer of the systems and the equipment in the building, to the control systems in the BMS, to the communication layer that is IP, you need millions and millions of transactions per second in order to make this all work. Guess what? The internet can do that? No problem. No problem. 10 million transactions per second? No problem. That's faster than the entire Visa network. That's what you need. And then finally, down in the component layer, all of us. It has to work for us. So you have to have a use of standards. We see BACnet there. Good old ASHRAE standard. This is really important because none of it, honestly, and I asked 25 different companies, do you have BACnet integration? And all of them said either yes or we're getting there. All of them. So it's on everybody's radar. Everybody knows that they need to integrate with the building system. The question is, how long will it take to do that? And what market systems will emerge to create these virtual power plants? How fast can that go to create the flexibility across this entire building portfolio? So I'm just going to give you a very, very quick, maybe 2 minutes here. I just want anybody from the audience to point at one thing on this slide and say, I want to hear about that. Okay, go. Anybody, raise your hand. Because I'm not going to drill the whole slide. It would be impossible. Does anybody have an interest in something up there?
Digital twin modeling.
Digital twin modeling. Digital twins are super cool. A digital twin is when you take a computer and you model the entire building and its history digitally so that you can forecast what the building will look like tomorrow, a month from now, 2 months from now. If an outage happens, how will the building react? If a heat wave happens, how will the building react? If an X, Y, and Z happens, what will happen? That's what a digital twin does. And when you have a digital twin, that's an emerging innovation. There are digital twins today, but if you have a really good one, then you can predict how many people will be in the building at what time of day, what their needs will be, and you can model the energy around them. All right, anybody else? Yes, sir.
I'd say the
Grid-tied thermal storage. Grid-tied thermal storage. Grid-tied thermal storage is where you have a large boiler system or a large hot water system, we're going to call it, and you pump it up and you pump a bunch of thermal energy into it at the very top of its capability curve, and you really only need this much, but you pump extra thermal in, you get those BTUs in there, and then you let it ride down back to its normal operating criteria through an energy crisis until you get down just below its most, functional state, down to the very lowest that it would be. You need an artificial intelligence system to tell you how to model that and what to store it at most efficiently over the next, let's say, 8 to 12 hours. All right, any more? Any other takers? Yes, sir, you. A customer energy market. You want to sell the energy in your car. You only have to go 5 miles to get home, and you keep your car plugged in all the time, and you've got 80%. At 80%, you've got something like 60 kilowatt hours in your vehicle. And so you're willing to sell it for 10 cents a kilowatt hour, even though you paid, let's say, 15 cents a kilowatt hour. You want some of that money back because you just don't need it. Or let's say you don't sell it for less than it was worth. Let's say you sell it for 25 cents per kilowatt hour because you're not feeling any philanthropy in your bloodstream at that moment. You want extra money, and so you sell that to one of your neighbors. You can do that. There are practical applications today. The Brooklyn Microgrid project actually did that. It was using a blockchain. And I was the chair of the interoperability standard for my IEEE for blockchain for energy. I can tell you it definitely works.
I was looking to the blockchain as it was to Internet of Things.
Yes, sir.
A long time ago, and they ended up doing this like scam. It's like,
yeah, don't pay attention to the scam. You really got to be careful. If you want to talk afterwards, I'm happy to give you some advice. But I would tell you that these kinds of consumer markets, they are available, but they're also really difficult to implement because right now in most states in the United States, as Matt will tell you, it is illegal to sell your energy to somebody else unless you're a utility. You need a license for it. So it would have to go through your utility so that because they own that license. California is experimenting with some of that right now. And anybody else experimenting with that? I don't think, not at scale. Any? Yes, sir. Let me go over here and then I'll come back to you. Yes, sir.
Building system integration would be virtual.
Building system integration with virtual power plants. I'm just going to go back 2 slides. This is what that is. You got your BMS, and your BMS has all your controllable resources, your VFDs, your chillers, your heat pumps, and you can control them in the building management system. You just need someone to represent your interests in the grid. So it's either going to be the local utility or going to be somebody who aggregates up your interests as a building owner or as a building controller or as a building manager. You just think of a building manager with 2 million square feet of commercial building space. They need somebody. I'm like, wow, I've got a lot of space. I have a lot of equipment that I could move around. Can I sell that into the energy market? And the answer is yes. Yes, sir.
maybe something called grid edge system automation.
Grid edge system automation. Grid edge system automation is really interesting because you have feeders, which is the name of a circuit that feeds buildings and homes and everything out there. So it's called a circuit. And out at the end of that feeder or that circuit, there's some equipment. And the equipment, there's things called reclosers, so that if somebody hits a light pole and knocks down a power line, that it shuts the power off by opening the circuit and preventing a sneaking wire on the ground that could kill people. That's called grid edge automation. Another type of automation is called a tap changer, so that if everybody starts turning off their lights really quickly, that the tap changer changes the voltage really quickly on the line by changing the number of windings that are exposed in the transformer, and it brings the voltage up or down based on the loads as they move around during the day. That's more grid edge automation. Those are both very, very common. If you coordinate between the building and the grid edge automation, there are services there that you could provide to the utility with the equipment in the building that they're willing to pay for.
Maybe a bit of fire, so really about operations.
Say it one more time. Yeah, anti-islanding. So islanding happens when you have a very large generation resource and suddenly it's cut off because of some problem with, like, let's say voltage, and you don't want that very large solar resource to stop feeding into the grid. And inverters, and this is because solar panels, they're DC resources, and unlike AC resources, thank you, Nikola Tesla, DC resources, they have square waves, and they don't play really well with AC systems. And so the inverter has to turn that square wave that the solar panel gives into a nice friendly wave. And your inverters, as of just a few years ago, the inverter that changes your solar panel into a grid-friendly thing, if they used to have a standard that said if you run into voltage problems, then disconnect right away. And now they don't do that. So an anti-islanding means that you're preventing that resource from disconnecting it with its entirety. Yes, sir? No, it's, sure, yeah. Anything out of the grid edge is grid edge. You know, I mean, sorry, I'm using a cursive thing there, but the idea that if you have something out there and you want to automate it and you want it to interact really well with the grid, then you have to have a standard. And that standard is usually what's called IEEE 2030.5, 2030.5. And that standard lets your building management system listen to what the utility is saying, and you can tell the utility what you want to tell the utility as well. And so you can tell it about all the devices behind your building management system curtain. And there are other standards too, IEC standards in Europe, if anybody's interested. Yes, sir?
Which entity will be responsible for this platform integration? I know there's multiple entities that have to work together.
Yes, sir.
Who would?
I'll say that there are multiple entities. I'm just going to go down the list. The first entity is the utility, because the utility doesn't want you messing around with their grid. And so you need to talk to them if you're going to be building a tool that will respond to grid signals and do things without telling the utility. You should definitely tell them, number one. So the utility. And then number two are aggregators. And an aggregator is someone that is interested in your load because they want to sell it in the market. And they make money on that. Did anybody see that big snowstorm that happened in Texas last week? The price of power went to $10,000 a megawatt hour. That's $10 a kilowatt hour. There's no one in this room that pays more than 50 cents per kilowatt hour. Imagine if you had not just 10 times, but 20 times higher. Imagine going down to 7-Eleven and having to pay $120 for a gallon of milk in one 24-hour period. Would you buy milk? Lots of people bought milk that day. It was called power in the ERCOT. Lots of people were buying milk. Okay, needed it real bad. There were 25,000 megawatts that disappeared from their grid because of outages. So it was a real rough time in ERCOT. So the answer is also an aggregator. And then the third is the building management themselves, that you want to speak with them, because every tree starts with a seed. And you can talk to me. You can talk to me. If you're interested in this topic, please talk to me. That is my presentation. I have successfully and sneakily used up your questions. So thank you so much. If you want to reach out, you can find me at qgems.energy. Thanks so much. And actually, yes, you can reach me there. There are other ways to reach me too. We'll send that out. And if you're interested, just hit me up for my badge, and you can reach me that way. Thank you so much. Moving on.
All right. Well, many thanks to Sean for walking us through the building dimension. I'm going to start to zoom back out, and if you recall the sort of architectural layers that he walked us through, that top layer is that policy and regulatory layer, and that's the focus of this work product from GWAC that I'll speak to in a moment, and I'll explain why it's pertinent to buildings and why it's really important and critical path for us to unlock all the benefits and opportunities that Sean was just laying out for us. So I'll start with a little refresh on some of the sort of background and context, sort of laying the playing field for us here within the current state of the grid. Then I'll introduce this concept that we've been championing at GWAC, and that is this notion of systems thinking, and specifically systems thinking and applying it to the utility regulatory space. And we'll unpack a few tools that are systems thinking tools that regulators, as well as folks around the broader grid community, can really implement it in practice. We'll touch quickly upon stakeholder mapping and feedback loops, demonstrate the iceberg model as a systems tool, and then we'll really come back to some core principles and key takeaways for this all. So, Ron did a really nice job of laying out sort of where we are today. But there are three incredibly challenging and complex situations facing the utility grid at the moment, and in particular regulators. The first is affordability, right? Residential electric bills are increasing. The electricity prices are projected to increase 2 to 4% above inflation year after year. And this price increases ultimately vary by region. So some regions are increasing prices at a greater rate than others. And this is driven in part by a number of different factors. The aging infrastructure of the grid needing to be upgraded, but also because of electrification of buildings, transport, heat, but also because of reshoring of manufacturing and the advent of very large load customers, namely data centers as well. So data center demand, that last piece, driven by artificial intelligence, is continuing to strain the grid, right? There's a lot more capacity being requested by these types of resources than the grid has available at the moment, right? So estimates widely vary. It's tough to get a really precise forecast as to what may emerge in practice, but data center load growth is expected to increase about 14.6% between 2024 and 2030. And that's a 232% increase from the past decade. So this is a major new development that the utilities, regulators, and grid are dealing with all at once. And then finally, there is this dimension of not only just affordability, not only just load growth, but also resilience as a key challenge facing us in this industry. And wildfires is just one example. Of course, there's named storm events, the winter storms that Sean just referenced in Texas. But wildfire risks in particular continue to grow for utilities and their customers. Wildfires cost an exorbitant amount of money. This is not a trivial matter. This is hundreds upon hundreds of billions of dollars annually that are impacting our society and our economies, right? So what was historically a very regional and seasonal issue is now national and year-round, right? And so how do we think about dealing with these triple challenges? And how do we think about buildings as a part of the solution in terms of a tool and a toolkit going forward, right? So we mentioned this a few times now, and I think it bears repeating. We're moving from a very analog, one-way central station power environment to an increasingly digital, multi-directional, and clean, decentralized energy network. And this is a really big change, right? This is a change that is upending and shifting a paradigm of how we've run the electricity system for hundreds of years, right? And it's only been in the last several decades where new technologies have emerged and that have enabled this possibility, where the generation is moving from central station, as Sean described, to the edge of the grid where the power is consumed. And that's where buildings have a role, right? Buildings themselves can be a resource, a tool in the toolkit, a part of a virtual power plant, and also critically flexible load. And for us to create an increasingly dynamic and agile electricity network, we need every node in that network, including buildings, to be flexible, right? To be able to respond to different signals on the grid, to reduce their load when that's going to be advantageous, both to the building occupants, because they'll save money, but also to the grid as a whole, because even those not situated within that building, or that cluster of buildings, can save a ton of money if we all coordinate our actions and reduce the amount of investment that we need to put on the grid overall. But really, none of that can actually happen in practice unless we have the right regulatory landscape and policies in place in order to accelerate that, enable that, facilitate that. So regulation and policy can be a barrier to this kind of progress, to this kind of future grid state, or it can be an accelerant. It can be an amplifier. It can enable it to happen. Right now, what we have in front of us, unfortunately, is a regulatory innovation imperative. We need innovation not just in the technologies we've already seen, and we see in the expo floor here, all the building controls, the opportunities that are present. We need innovation within our policy and regulatory construct to catch up our regulatory system to advance it from the 1870s to 2025, right? And so what this illustrative diagram shows is that we have technology accelerating at an exponential curve, and we have organizational change, including regulations, advancing logarithmically. So we have a gap between technology and sort of our rules of the road, our organizations and institutions. And that gap widens over time. And what's required is a step change, right? An opportunity for organizations like utilities, but also regulations to reset, to catch up to this new technology baseline that we're facing. And this is true in any industry, right? But it's particularly acute now here in the electricity sector. So enter the need for a new way of thinking, right? And this is where systems thinking for regulators comes into play. So we have three different types of policy problems as we describe them. And these are problems that can be adapted and transposed, projected onto different industry types, right? You could bring this to the building sector if you'd like. But for this presentation, we're really focused on our utility regulators because they're the critical path for us to unlock this bidirectional energy network future state, right? So three types of problems: simple, complicated, and complex. Simple problems, the solutions there are fairly straightforward, right? We can just look at best practices, just fairly straightforward in terms of how you unpack and solve that. Complicated problems are a different order of magnitude. Here we need some expertise, we need some analysis, and some modeling exercises, relatively straightforward, can isolate the problem, solve it. Complex is a different beast entirely, right? This is an emergent challenge. It's a whole of system approach that's required. And there's lots of feedback loops and interactions. So if you squeeze one part of the balloon, it's impacting other parts of the balloon as well. So the solutions that we bring to tackle complex problems have to be holistic and systemic rather than focused and narrow, right? In order to achieve optimal outcomes in the end. And increasingly what we're seeing, because the grid is so complex and because of these new dynamics emerging that we've been talking about today, utility regulation is a complex problem set. And unfortunately, we're continuing to use simple and complicated solutions to try and solve complex problems. And it's resulting in a lot of suboptimal outcomes across the entire system overall. So what we need to start to encourage our regulators, other industry stakeholders that help to shape and build out the policy layers, regulatory layers of the future grid, to start thinking more systemically, right? And so systems thinking is a broader discipline. It's not just applicable to the energy space, but it's about understanding complex interdependent systems by mapping relationships, by understanding feedback loops, constraints, emergent behaviors, rather than just looking at individual components in isolation, right? And this is certainly true in the built environment as well, right? When you think about a building, you can't just isolate for one part of that whole system. You really need to be thinking about building systems as a whole, how all of these systems that you're integrating work together. It's the same for the regulatory environment, right? And when we talk about grid architecture here at GWAC, what we're really doing is we're taking systems thinking and those same principles and we're applying them specifically to electric power systems. And that's where those layers of that GWAC stack come from, is really a systematic systems thinking approach to how to continue to evolve this network for the benefit of society overall. So when we talk about systems thinking for regulators, there's four sort of core principles that we think about: wanting to have a holistic view of the grid, wanting to focus on these interactions and interfaces. We want to be explicit about the complexity. Too often it's a desire to sort of run away from that complexity, to try to oversimplify and constrain. And increasingly, you can maybe get through a problem pretty quickly, and you think you have a solution, but ultimately that creates more problems down the road. So just embracing that complexity to understand the problem and the root causes so that you can design a better solution. And then designing for emergent needs. We're talking about how fast things are changing, right? Technology is progressing very quickly. So anticipating changes in the future state, not solving for a problem that occurred 5 years ago, but anticipating being flexible and agile for challenges that may emerge in the next 5 to 10 years going forward as well. So let me just give a couple examples of like, what does this actually look like from a regulator perspective within a regulated utility environment? So a couple of systems tools I'll highlight. One is stakeholder mapping. And then the second one I'll spend a little more time is this a tool called the iceberg model diagram, and kind of break that down. So stakeholder mapping is relatively straightforward. It's just understanding that a holistic regulatory approach recognizes that there's an interconnected nature of utility systems, policies, and markets. And all of these nodes are working together. All of these stakeholders have a impact, not just on the shaping of the outcome of the regulation, but also downstream, once that regulatory decision is made, how all of these stakeholders interact with it and with each other are really what the manifestation of that is, right? And so simple diagram here, we've got regulators in the center because that's the target audience for this discussion, but we have utilities, we have communities, which includes the built environment, right? Buildings, NGOs, legislature, customers, DER providers, governor's office, utilities. So just acknowledging that there is this complex web of interactivity that ultimately shapes what regulation looks like in practice, right? And acknowledging that's key. So why interactions matter? As I said, regulatory outcomes are shaped by the interactions between these parties themselves, not just the rules, right? The rules are not self-effectuating. They don't exist in a vacuum. They get flowed through a multitude of interactions between the stakeholders I showed on that last slide. And if you have blind spots, that can really impact affordability, that can really impact equity in terms of how the grid is experienced by everyone. And it can really result in a lot of stakeholder pushback. And systems maps, where you start to map out the stakeholder interactions and what's involved there, they can reveal some of the underlying incentives. They can identify leverage points where you can have a real impact on outcomes. And they identify risk in terms of how you want to navigate and identify what's the best path forward. So this slide, it speaks a little bit to incentives and feedback loops. And it's just to state it really simply, you can have positive loops, virtuous cycles, or negative loops, right? So when we think about DER adoption, if we're setting that up effectively, as DER adoption grows, we have increased system flexibility, we have increased resilience on our system, and that in turn helps to facilitate increased DER adoption. That's a positive loop, and DER adoption grows over time. Negative loops can have the opposite effect, right? If we're not treating the built environment or DER appropriately, we can see an underinvestment in this really valuable resource because we have not the right signals being sent or the right market opportunities being extended. So moving to the second tool in action example, the iceberg model. So what's the iceberg model? Well, it's a applied systems thinking tool that really tries to identify different layers of sort of causal impacts, right? So the very top, we have this events layer. This is the sort of part of the iceberg that sticks above the waterline. It's the part that's visible, most immediate. And so there's this illustrative example that's reflected here that has nothing to do with buildings or the electricity network. It just has to do with explaining how this systems tool is intended to illuminate things below the surface. So the event here in this particular example is I caught a cold, right? That's what's at the events layer. That's what we can see above the waterline. And the sort of immediate action there is often a react, right? Just below the surface, we have patterns and trends. So what are the trends that have been there over time, right? So I've been catching a lot more colds when I've been sleeping less. And that's more of the anticipate sort of action statement there. One layer below patterns and trends, we have underlying structures. So what has influenced the patterns? What are the relationships between the parts? So I'm having more stress at work, I'm not eating well, I have difficulty accessing healthy food near my home or work. And that's a design type of action statement, right? So now we can start to think about how we're designing these underlying structures that give rise to the events at the very top. And then finally, at the very base of this iceberg model, we have mental models. And this is sort of the core, almost sometimes unconsciously accepted truths about a system that give rise to events at the top. So in this particular example, what are the assumptions or beliefs or values that people hold about the system? What beliefs keep that system in place? So here in the I call it a cold example, maybe we have a mental model that's career is the most important thing. It's the most important piece of my identity. Healthy food's too expensive. Like I don't have, time to get proper rest. It's really unmotivated. And all of that mental model gives rise to some of the layers above it as well, right? So how do we apply this to the electricity system? How do we, get regulators starting to think in these systems kinds of ways? Applying it to a case study of resilience. We talked about wildfires being a real issue all across the US. So that events layer is we've got a wildfire, we've got a severe storm that's resulted in widespread outages, we've got downpoles, the distribution system level. Patterns and trends, we're below the surface of the water. So we've got a frequency of wildfires and extreme weather events is increasing. Customer outage frequency and duration is also increasing. And the costs for storm and wildfire recovery are putting upward pressure on rates. One layer deeper still, now we're looking at underlying structures, right? So we've got climate driving more frequent extreme weather events. We've got grid hardening and a response to that's now driving up costs while offering sometimes suboptimal performance into what we actually want to see from a resilient system. When we have wildfire events, often utilities are shutting off their transmission lines in order to stop the ignition of a wildfire. But while that addresses wildfire risk, it also can disrupt customers and create other safety impacts in other ways. Folks that rely on electricity for oxygen, folks that rely on electricity to make sure that they're staying in a comfortable built environment so they're not under duress. And so finally, at the mental model layer, at the base of this iceberg model diagram, this traditional focus that we have in our industry, in our utility industry, on sort of grid reliability and resilience, and that's being much more grid-centric and sort of focused on a system that lives far away from the customer, rather than thinking about energy service reliability and resilience, really a customer-centered view. So this top-down traditional approach that we often employ is increasingly fragile and flawed in this new emerging dynamic. And as we start to embrace more bottom-up approaches centered on the end-use customer, this will help enable continuity of energy service even when that broader grid is down, right? The building's lights stay on, the cooling system stays on, and folks remain comfortable. And that's ultimately what we all care the most about, not whether the grid is on. We want our lights on and we want to be comfortable in our buildings, right? So with that, we can move to some core principles and some key takeaways. So some core principles that we want to impart on regulators and all stakeholders that have a stake in this energy network of the future is that we want to be thinking about both horizontal and vertical whole system perspectives. We want to be thinking across silos horizontally, but we also want to inquire beneath the observed events, as we just demonstrated in that iceberg model diagram. The interconnections and interfaces matter, sort of how these regulations, how these policy layers really push forward opportunities for increased affordability resilience. And we need to pay attention to the seams, sort of where these silos mesh with each other is often a really important part of designing good regulatory and policy outcomes. Feedback loops drive behavior. So what you measure and reward often determines how the system behaves. So what are the incentives that we're extending to our utilities in our jurisdictions? How do they make money? And is the way that they make money today optimized to what we want to be seeing out of the grid of the future going forward? Emergence happens, so expect the unexpected, create a flexible and agile environment so that you can be continuing to keep up with that technology curve. And then boundaries create clarity, right? So we want to be defining roles so that we have clarity and accountability and responsibility, but we need the flexibility to be adaptable going forward as well. Finally, multiple perspectives and rich solutions. So it's not someone in an ivory tower setting out rules that they think is optimized. It's really about bringing the whole community together, not just industry stakeholders that are building the tech that gets deployed, but community members as well that are the ones impacted by it and hosting that infrastructure. Time horizons matter, so we got to think in trajectories, not snapshots. We'll always be behind where we want to be traveling. And then we have to leverage the structure, right? Not just the symptoms. So we don't want to just focus on the tip of that iceberg. we want to be thinking about all of the layers of it and moving this whole system forward in a co-optimized manner going forward. So with that, really appreciate the time and attention. Thanks so much.
All right, right on time. We have a few minutes for questions, so we'll open it up. If you have a question or a comment or even a use case that would be of interest to discuss. Yes, sir. Nice and loud. That sounds like you're doing.
We've got one of these. Yeah. Yeah, it's a great question. So part of my background, I spent about a half decade at the Hawaii Public Utilities Commission. So state of Hawaii, for folks that aren't familiar, has some of the highest adoption of distributed energy resources on the entire planet, save Australia. And so during my time at the commission, I was in the privileged position of having to work on all of these kind of technical, economic, and policy considerations about how we start to integrate DER, right? And so, it's a very challenging landscape, but Hawaii has been dealing with this for some time now. And progress is uneven, but that would be one jurisdiction I would say it's been dealing with high penetrations of DER state for a very long time, and really been working on how do you provide revenue opportunities for aggregations of DER in the built environment, as well as distributed solar and storage, right? On the mainland, as they would say, we have a few leading jurisdictions across the country. So, you look at from an ISO perspective, New York ISO, New England ISO, having a lot of opportunities for VPPs to be bidding into those markets. And FERC 2222 is a piece of federal rulemaking that enabled that to happen, right? So going back to my point is, prior to the FERC issuing its order number 2222, these virtual power plants did not have an opportunity to participate in wholesale markets and monetize that opportunity. So just underscoring the importance of regulation and all this, right? And then what we were seeing is really across the country, even at the state level, emergent opportunities to be building up VPP programs. So Colorado, Massachusetts, other states really across the country, California certainly, are starting to push forward with some really interesting approaches. Now, I think we still have a long way to go, and there's a lot of improvements that can be made even in those programs that are live today. And that's a lot of what I work on and GWAC works on in terms of helping to facilitate and get to a place where more of those opportunities are present, and they're present in a way that's like embodying interoperability and open standards, so that folks interacting in these markets can do so in a very consistent way, regardless of what utility they're interfacing with, regardless of what state or ISO market. Ideally, there's a lot of uniformity and standardization as to how this implements.
I want to add in New Jersey. Just a week ago, Governor she required the Public Utility Board of New Jersey to come up with virtual power plant solutions in 45 days. And that, in the utility sector, 45 days, that's like light speed. You would leave that order, 45 days. So you should check that out.
Nothing like a pending deadline to light a fire under people's pants.
There's like a 45 and 90 and 180 day requirement around coming out. But you check it around.
Yeah, if you just look at how long FERC 2222 took to get from concept to reality, years.
Yeah, progress is definitely measured in years, not months. But I would say, depending on where there is, how we define there. I think, some meaningful catalyzing activity can happen in a couple months, and then ideally that's kicking off a much more long-term operationalize the process by which long-lasting, products can be unlocked.
Any other questions? Yeah, Chris.
So a lot of decisions right now are made off of price signals. Do you think there are other signals that we should be looking at to control some of this equipment differently?
Yeah, I mean, price is important. Sorry, I'm
No,
not to be to jump in there. I think price is really important. I think there are some schools that think that you can do a lot of things through price alone. There's other schools that really think about the grid and decomposing into a number of different grid services, right? So price may be really great for energy and sort of balancing energy, but we may need other types of maybe more physics-based signals to be responding to in terms of providing frequency response or voltage response, right? So power electronics in in buildings, in these devices are very powerful, right? And they can respond autonomously to changes in frequency, changes in voltage. And if we can, then complement that autonomous response, because that's the speed at which the grid needs the service, then we can sort of settle the market implications of that backend, right? If that's a grid service that gets provided, autonomous real time, like nanoseconds, milliseconds, then on the back half we'll settle that in a slower pace that you'll be compensated for providing that service, right? So not just price, but other physics-based signals that are, I think, really important as well.
Yeah, and I think a lot of that comes down to how fast, what's the response time needed? Because if you look at price has a duration associated with it, which is called the pain point. At what point going in as the price changes, are you going to be able to react and make a decision on what you're going to do? But that's measured in minutes or hours sometimes, but the grid may need something faster than that. That's in the sub-minute range, and price isn't that, unless you start getting into some tools that can negotiate price in a transactive process at the speed of electrons. And we're not there yet. So I do think that there are going to be signals like a demand response signal coming from a building that offers up a load shift within seconds or maybe a minute or two that would be calculated, as Matt was saying, on the back end as a price in like a clearinghouse. But in the short term, it's, hey, I can shed this load, this many kilowatts, and I can do it on this phase, because that's more than just money. It's the electrons and where they are and how you're balancing the load.
I want to add to that there's these grid signals today. The grid has to have these things called regulating reserves, and if the grid is, like we have 60 hertz here, like we can plug in 60 waves per second, right? If you're over in the UK, it's 50. And that 60 waves is really important, the frequency, because if it starts to ride a little low, like 59.9, 59.8 kind of thing, the grid is listening. There's this really important term to a grid operator called the area controlled error. And it's like, well, if I even know some, even just at the top, a little bit, it's like you have to increase the torque on all the generators that are functioning a certain percentage. And so that's called grid. And so there's a mechanism right now, what Ron is saying, you just have to sell your virtual power plant as regulated. Say, hey, I can do that. And so if your equipment is already driven, why don't you pay for that? And so that's the point, is that the physics side of it has been studied for 100 years, and just the economic stuff that just came out in like 2008, 2009, when people started thinking about that. But the really big project, P&L, Pacific Northwest National Lab, called the Pacific Northwest Smart Grid Demonstration Project. I was very honored to be one of the system architects in that project. And it was super cool because we're like, hey, let's get the physics and we join together with the economics, what would happen? And so we started to see what happens when we cross those signals. And guess what? The system worked way better, way better. So it's not just a little bit of change. It's like, it's not just a price signal. I'm glad you said that, because I think, and this is the last thing I say is, maybe not, but it's about people. It's all about people. We're this stuff matters unless it's about us. Well, the ants don't care about that stuff. It's about us. For people. So your signals, the way that you're happy with the grid that we get and the building services you get, that's what's important. Let those signals be the controller. And then, oh, am I unhappy about power? Would you rather have the heat or would you rather have the money? Would you rather have the cold? Would you rather have the air? Would you rather have the money? I mean, some of those trade-offs they happen right now, especially in this control area. Nevada has the largest demand response program, one of the largest in the whole United States. And they can turn off a whole power plant, 1,000 megawatts, just by turning these storm stats up. Then we have high winds. That was ridiculous. They've had that program for more than 15 years. So it's not like those trade-offs aren't made. It's just you got to connect them there. So I think the mechanisms are there. You know, you just got to have two together system. I think it can work.
So I want to add to that a little bit that not only is it the balancing of the load, but in my experience in certain countries around the world, it's also the power quality. So that if your power quality diminishes, like you get below 59 hertz or 59.5 hertz, that power quality can have a direct effect on switching power supplies and equipment. And so then you start seeing decays of power supplies and your BAS equipment dies because you're not having good power coming in. And that happens, much faster than price signals and even much faster than that 60 hertz wave that you have to adjust. I've seen this. I actually had an incident happen this morning where we were talking in the last session where we lost control of a building because we didn't have a UPS on a unit that there was a power fluctuation and it didn't come back on when it should have. That happens. It happens. And, we're pretty good in the US about keeping that power quality and power factor and phase balancing good. But if you've got a dirty source of power coming in that's not handling that, the utility has to come back and make up for it and ramp up. And as you were saying, if something bad happens, it's really bad. I mean, like you'll see it from outer space when it happens. It's really bad. Blowing up generators is not a good thing. Not a good thing. With that, I think we will. Do you have another comment? With that, I want to thank you all for sticking around. I know this is kind of a little bit of an esoteric topic. It's good for us to get feedback. Thank you very much. Please feel free to come up and chat with us, and we'll let you get on to your next party. Right? Isn't that when the parties are tonight? Thank you.